Hello, this is Dr. Tom with a presentation on bolted connections and specifically stiffness and strength as part of our review of machine design. Material happens to be in the reference handbook under the section Joints and Fasteners. So let's get started. Okay, there's typically two types of bolted connection. One that uses what is referred to as a cap screw, which it goes into a threaded member down below, and the other is a typically partially threaded bolt, as shown in these figures, and they can have lots of different things in them. But one of the most important design considerations is the stiffness or spring constant or spring rate of the assembly, where if it's not stiff enough, the joint will separate under the load. So under an external load P, the cap screw or bolt acts as a linear spring where they elongate a distance delta. So that load P and the elongation can be related by the equation P equals K delta, where K is the spring constant. It's also called the stiffness. See both of those terms. So if we solve for the spring constant K, we get P over delta. Now, recall from our solid mechanics review that the change in length of a member under an axial load is given by the expression delta equals PL over AE, where L is the length, A is the area, and E is the modulus of elasticity. Well, we can rearrange that to put P over delta is AE over L. Well, we can compare those two expressions, and what now happens is that the spring constant or stiffness K becomes AE over L. Now the cap screw is typically threaded along its entire length, so it's really only got one term, designating the area T. A sub T is for threaded, and we will use A sub UT for unthreaded. It's length L sub T. So for the cap screw, its stiffness K is AT E over LT. Okay. Okay. Now, the bolt has a portion of its length threaded and some portion unthreaded, so it has two spring constant or stiffness expressions, K sub T, A sub T E over L sub T, K sub UT equals A sub UT E over L sub UT. Okay, so these two stiffness add together like resistors in parallel. 1 over K equals 1 over KT, 1 over KUT, and when you rearrange through the algebra, you get K bolt is KT times KU over KT times KUT. So let's look at an example here. We have a threaded length of a 3/4 10 UNC course. A steel bolt is 2.5 inches and the unthreaded is 1 inch. Then determine the spring constant or stiffness of this bolt. Okay, so we start with our equation of K bolt and our two individual K's, K sub T and K sub UT. Now they have a table in the reference handbook for this particular size bolt. The tensile stress area A sub T is 0.334 inches squared, and we can find, of course, the unthreaded diameter is just pi d squared over 4, where d is the diameter of the bolt, in this case 3/4 inch, 0.75, and we get 0.442 inches squared. So now we can put the areas and the E for steel, 30 million times 10 to the 6 divided by the lengths, length of the threaded portion 2.5 inches, length of the unthreaded 1 inch, and we get the two values that you see there. Note the powers, the K sub T is about 4 times 10 to the 6, whereas K sub UT is 1 times 10 to the 7. So really what you have down there is 13.3 times 10 to the 6. That kind of helps in your math. So now put that into our equation for the stiffness of the bolt. So we've got the two numbers are multiplied together in the numerator, they're added together in the denominator. Basically you'll have a 10 to the 6th fall out there. So basically what you have is treat that 1.33 as 13.3, and you should get 3.08 times 10 to the 6 pounds per inch as the spring constant or stiffness of the bolt. Well, let's suppose that instead of being a coarse threaded bolt, it's a fine threaded, so it's a 3/4 16 instead of the 3/4 10, and so determine the stiffness of this alternate thread design. Okay, well, we still have the same equation for K bolt and the same equation for K sub T and K sub UT. The difference is that the tensile stress area A sub T for this particular bolt is 0.373 from the reference handbook, but the A sub UT is the same as for the coarse because it's the basic diameter of the bolt, 3/4 inch. So we have a new K sub T of 4.48 times 10 to the 6 pounds per inch. Of course, our unthreaded stays the same, so we can go in and calculate A sub UT is 0.442 and the 1 inch, so it's still the 1.33 times 10 to the 7th pounds per inch. So substitute that into our equation for K bolt, and we get 3.35 times 10 to the 6 pounds per inch. And just for curiosity, let's compare that. The UNF divided by the UNC, 3.35 times 10 to the 6th divided by 3.08 times 10 to the 6th, and that's about 1.09 or almost about 10% more stiffness with the fine threaded instead of the coarse. And that's all part of that tensile stress area value. Okay, let's talk about the stiffness or spring constant of the members now. So for a bolted connection, there's always going to be two members in the assembly. You can also have various other things like washers, and of course you'll have the bolt. And there's all kinds of other things you need to take into account, which we're not going to here, stress concentration factors. And there also can be a gasket between the two members, so all of that comes into play. So if you look at all of these together, you end up with this sort of string of numbers here. 1 over K for the members is 1 over each one of them. So K1 through however many you have, 1 to N. But what is very important to notice here is that the element with the smallest stiffness will dominate the overall stiffness of the overall assembly. Okay, so the weakest, as they say, the weakest link is the one that governs. Okay, for the bolt strength and bolt preload here, bolt strength is denoted S proof. Proof load F proof is divided by the tensile stress area A sub T. Or rearranging, the equation you have in the reference handbook is F proof is S proof times A sub T, although they just call it FP and SP. I like to go in and spell things out. It's easier to identify things. So then the proof strength is the maximum allowable stress in the bolt before a permanent set is developed. This occurs approximately at 90% of the yield stress of the bolt material. Now, depending on whether the joint is to be a permanent joint or will be disassembled, these are the guidelines for the preload. If it's going to be reused, you go to 75% of the proof, and if it's a permanent connection, you go to 90% of that proof load. And what is always comforting is that if a bolt is weak, it will usually fail during the application of the preload. So it'll break when you're trying to assemble it. That is definitely comforting. You sleep at night on that one. Okay, now we'll talk about the external load. External load here designated P, shown in this following diagram of a bolted connection here. And this is essentially the figure that's in the reference handbook. I've redrawn it, avoid copyright kinds of things. Took a while to draw that, but I'm very proud of it. Now, however, the load is not carried entirely by the bolt. The members carry it. In fact, they carry a lot of the load, as we're going to see. So therefore, the total external load P is divided between what is going to be carried by the piece of bolt, and piece of members. So the elongation of the bolt must be equal to the compression of the members. And so what we have is delta's P bolt over K bolt, which is equal to P members over the K members. Those two ratios have to be the same value. So we solve for the load carried by the bolt. The P bolt is K bolt over K members times P members. Or you can rearrange and get P members as K members over K bolt times P bolt. So you get either way. And now you can substitute that into our basic equation using the P bolt, substituting the P bolt equation for the members. So you get P bolt times K members over K bolt times P bolt. So you can factor out the P bolt, 1 plus K members over K bolt. And if you find a common denominator, you'll have K bolt plus K members over K bolt times the P bolt. So there's a little algebra involved here. And so this is the equation. You can now rearrange it to where now solve for P bolt, and so now you have K bolt over K bolt plus K members times the external load P, and this equation is in the reference handbook. Okay, similarly you could rearrange for the P members, similar equation, but that's not in the reference handbook. And to simplify things is a joint stiffness constant, which is labeled C, is defined as the following. So it makes things a little bit easier. They can give you this value in the statement of the problem: K bolt over K bolt plus K members. So therefore, the load carried by the bolt, this was in the first edition of the reference handbook, but for some reason it got lost in the second edition. I don't know. P bolt equals C times P. And so similarly, by the members, it would be 1 minus C times P. So those were two very important equations that somehow I don't know whether they left them out intentionally or just they did some rearranging and just lost them in the shuffle. I don't know. Okay, so taking the bolt preload into account, the total load on the bolt and the total load on the members can be expressed as the following. The bolt portion of the bolt is the P bolt plus its preload, so that's CP plus the F preload. Again, depending on whether it's a permanent or a reusable joint assembly. And the members is going to be the members minus the preload, so that'll be a 1 minus CP minus the preload. Okay, so note that the force on the members must be negative so that the joint does not separate. So you need to count it when you get through and find the force that's there. Check to see that 1 minus C times P minus the preload is less than 0. And we will do that in examples. Okay, it's also interesting that experimental results indicate that, in fact, the members of a joint take as much as 80% of the external load and the bolt only 20%. So that's very revealing. Okay, well, let's look at an example here. We've got a half 13 UNC steel bolt. This particular one is threaded along its entire length of 3 inches. That's just to make the math here a little bit easier. And the stiffness of the members is given to you as 5 times 10 to the 6 pounds per inch. Then determine the joint constant C. Okay, well, we need the K bolt, which is K sub T. It's all threaded, A sub T, E over L sub T. From the reference handbook for this particular bolt, the tensile stress area is 0.1419 inches squared. So therefore, using steel, E for steel, we get K bolt is the A sub T, E over L sub T, and that comes out to be 1.42 times 10 to the 6 pounds per inch. Okay, so now we're given the K members, so now we got the K bolts, so put those in, do the arithmetic. Again, there's a 10 to the 6th everywhere. So this comes out, of course, to be non-dimensional, 0.22 if you do the arithmetic. Okay, now suppose in this particular problem, this bolt of example 3 is a grade 5 bolt. Determine its total load on the bolt. So we're going to use the joint constant that we just found, 0.22, and we're going to assume the joint will be a permanent joint. The total load, the external load, is 4,500 pounds. Okay, so since the joint's to be permanent, the recommended preload is 90% of the proof load. The proof is S proof times area tensile. From again the reference handbook, the tensile stress area for this particular bolt is 0.1419, and a table not a page over, the proof strength for a grade 5 bolt of this particular size, I think it's 1/4 inch to 1, is given as 85 KSI, 1000 PSI. Okay, so the proof is S proof times A sub T, so we got 85 KSI or 85,000 PSI times 0.1419 inches squared, comes out to be 12,062 pounds. So now we can multiply by 90% to get the preload, so we get 10,856 pounds. And if we use the joint constant from example 3, we have the bolt is CP plus preload, so 0.22 times the 4,500, P is the 4,500, plus the 10,856 gives us 11,846 pounds as the force on the bolt. Now, as we said, we need to always check to make sure that the force on the members comes out to be negative, and it does. It's 1 minus C times P minus the preload. And so if you do that arithmetic, you get a minus 7,346, which is clearly less than 0. So we're okay in that department. Okay, one last topic here, just I probably wouldn't even cover it if it wasn't used in a solution in one of the NCS practice problems here. The relationships among these various terms with a bolted joint can be depicted on what is called a joint diagram, sort of a graphical approach to this. That's sort of old school. As I say, from one perspective, the diagrams kind of yields the relationship, and from the opposite perspective, the relationships actually yield a diagram. Well, here the latter is used. And again, since this diagram is used in one of the solutions, I wanted to give you a correlation here. What we've been calling K bolt is just K sub B. What we've been calling K members is a K sub J. That doesn't work for me, but that's okay, K sub J. The external load P is F sub X. The preload is F sub P. The F bolt is delta F sub P. B, and then P members is delta F sub C. And again, I'm not sure those the B works the C. I'm not sure why, but that's it. So using the terminology there, here are the following 3 primary relationships in this joint diagram. The F sub X external is the sum of the 2, the bolt and the members. That's kind of what we're saying. And then the delta F sub B is the P times the KB over KB plus KJ. That's really the C that we had, right? And delta C is FX1 minus C. So that's kind of what that kind of comes down to. And the corresponding diagrams on the next page. And this one's really best I can do here is just just say this. One of the things is that if they're going to use it in the solution of a NCS problem, practice problem, it needs to be in the reference handbook, but it isn't. So what you have here is K sub B is the F sub P there, that vertical from the base up to the vertex, divided by the delta LB, the distance on the left, and then on the right divide by the delta TJ to get the K sub J. And then the way that triangle works out up there, delta, the F sub X is the sum of the two. One is the load carried by the bolt, delta FB, and the delta FC is the amount carried by the members. Okay, so that's the best I can do, folks, with trying to correlate with this joint diagram. Again, if it wasn't in the NCS solution, I would have never mentioned it, but I thought y'all needed to have a little bit of help with this. Okay. Well, that concludes the presentation. As always, thank you for allowing us to help you prepare for this exam.